Welcome, curious minds, to another deep dive. Today we're embarking on an incredible journey, looking back at the last 50-plus years of solar system exploration. You've sent us a really fascinating stack of sources this time, everything from, NASA's historical perspectives to insights on the politics of space, and even how our very own sun impacts Earth's climate. Our mission today isn't just to recap history, though. It's to really distill the most surprising facts, the underlying motivations, and the complex challenges that have shaped our push into the cosmos. It's a story of human ingenuity, scientific discovery, and, that relentless curiosity that has taken us further than ever before.
Exactly. And as we unpack this material, you'll find that exploring the solar system is far more than just launching rockets. It's this rich tapestry woven with threads of international cooperation, incredible technological leaps, and even the unique ways the public engages, with these endeavors. We'll uncover how this era of exploration truly began, some of the unexpected turns it took, and where it might be headed next.
So, when we talk about this incredible era of solar system exploration, what's the moment that truly kicked it all off? What was that first big step, really?
Well, according to NASA chief scientist Jim Green, the official beginning of this spectacular era, as he calls it, was marked by NASA's first successful mission to another planet. That was the Mariner 2 mission to Venus in 1962. It basically proved we could do it.
Right.
And from there, NASA adopted a pretty clear general paradigm for exploring celestial objects. First flyby, then orbit, then land, then rove, and finally the big one, return samples. Mm-hmm. Now, not every step is always completed for every object. Often it's due to the specific scientific questions or, technological challenges and, of course, financial hurdles. Money's always a factor.
And what a paradigm it's proven to be. I mean, think about it. In its first 50 years, NASA alone sent spacecraft to every single planet in our solar system, plus Earth's moon and several moons of other planets. Even Pluto, reclassified as a dwarf planet in 2006, got a close-up visit from the New Horizons spacecraft in 2015. But before all that, those initial flybys were truly foundational, weren't they?
Oh, absolutely. Those early flyby missions were crucial just for learning the basic physics of how to fly between planets. For instance, while the U.S. Mariner missions surveyed the inner planets, the Soviet Venera program famously targeted Venus directly.
Yeah, I remember reading about that.
And Venera 7 actually successfully landed and transmitted data for about 20 minutes before its battery gave out. I mean, Venus's environment is incredibly harsh. It was an astonishing achievement for its time.
Okay, here's where it gets really interesting for me, and one of the biggest aha moments from our sources.
Yeah.
The Voyager program, launched in 1977. These two spacecraft took advantage of this unique planetary alignment that only happens, about once every 175 years.
That's right, a rare window.
They went on this grand tour of the outer planets. One flew past Jupiter and Saturn, and the second visited Jupiter, Saturn, Uranus, and Neptune. What makes these missions so astounding, I think, is that they survived way beyond their expected lifetimes and are still out there, probing the edges of the solar system, sending back data from interstellar space. It just fundamentally reshaped our understanding of the outer solar system.
Completely changed the textbooks.
Speaking of reshaping our understanding, Mars.
Yeah.
Obviously, it holds a special place in our hearts and our exploration efforts. We've had these incredible successes like Curiosity landing in 2012 and Perseverance following in 2021. But what's the underlying goal that kind of unites these missions?
Well, the Mars 2020 Perseverance rover, which, built on Curiosity's very robust design, landed in Jezero Crater with a very specific, really ambitious objective. Basically conduct geological assessments, determine habitability, and directly search for signs of ancient Martian life. And the key part, coring and storing rock samples for eventual return to Earth. That sample return is the holy grail for Mars scientists.
And the idea of bringing Martian samples back, it isn't new, is it? Our sources mention planetary scientists have wanted samples back even before the Viking landers in the 70s. In fact, the National Academy of Sciences 2011 Decadal Survey made a Mars Sample Return Mission, MXC, they called it then, the Mars Astrobiology Explorer Cacher. It's number one priority for 2013-2022.
Yeah, and what's truly fascinating here, and kind of tells a story in itself, is the persistent challenge behind that desire. Despite decades of design studies and these missions being, like you said, top scientific priorities, plans for Mars sample return were canceled in 1991, 2000, and again in 2011.
Wow. 3 times.
3 times. The underlying issue is that these missions are incredibly complex, technologically really challenging, and, eye-wateringly expensive. NASA has historically struggled to find enough funds for ambitious human spaceflight and robotic science simultaneously, often forces a curtailment of the science ambitions.
It really highlights that constant tension, doesn't it, between what science wants and what reality financially allows.
Exactly that, a constant balancing act.
Okay, so moving beyond Mars, our sources reveal these incredible missions to other parts of the solar system, often pushing the boundaries of what we thought possible. The Cassini-Huygens mission to Saturn, that massive collaboration between NASA, ESA, and the Italian Space Agency, seems like a prime example.
It truly is a monumental mission. And the Huygens probe, part of that mission, successfully landed on Titan, Saturn's largest moon, back in 2005. Voyager's earlier flybys had shown Titan's atmosphere is mainly molecular nitrogen with methane, and it's packed with complex organic molecules. This unique chemistry, it's driven by solar UV radiation and cosmic rays, and it creates these complex carbon compounds.
It almost sounds Earth-like, doesn't it, in a very early, sort of primordial sense.
Well, in some ways, yes, and that's the key insight, really. Scientists think primitive Earth might have looked very similar maybe 4 billion years ago, before life started pumping out oxygen. The critical difference, of course, is Titan's extremely low surface temperature. Makes liquid water impossible on the surface. However, there's strong evidence a large subsurface liquid water ocean exists.
Beneath the ice.
Beneath the ice. Which means it could still be potentially habitable down there.
Fascinating. And it's not just planets and large moons that capture our attention, right? Our sources highlight that even objects like asteroids and comets, these kind of relics from the early solar system, hold immense scientific interest.
Absolutely. They're like time capsules. Robotic spacecraft have explored them, and the first material returned from a comet's tail from the Stardust mission yielded some truly unexpected results. Challenged what we thought we knew about how they formed.
Now, while we're busy exploring the furthest reaches of the solar system, sometimes the most profound insights come from the very center of it all. Our sources reveal some pretty fascinating truths about our own star, the Sun.
Yeah, the Sun. Formed about 4.6 billion years ago. It's classified as a G-type main sequence star, informally called a yellow dwarf, though, interestingly, its light is actually white.
Really? White. Optically white, yes. Our atmosphere scatters the light. Anyway, its core fuses approximately 600 billion kilograms of hydrogen into helium every single second. In doing that, it converts a staggering 4 billion kilograms of matter into pure energy.
So what does this all mean for us? I mean, that's an almost unimaginable amount of energy.
It certainly is. But here's a surprising fact for many. The maximum power density at the Sun's core is actually similar to that of a compost pile.
Get out! A compost pile.
Yep. It's the sheer volume and the sustained nature of the reaction that makes it so incredibly powerful overall. And importantly, especially for climate discussions. While the Sun does noticeably affect our climate over millions of years, think ice ages. The changes in solar radiation over the last century cannot account for the magnitude of recent global warming.
Okay, that's a key point.
It is. The sources emphasize that between 1750 and 2011, the increase in what's called radiative forcing, basically, how much Earth's energy balance is thrown off due to human-induced heat-trapping gases, was 56 times greater than the increase from the small shift in the Sun's energy output. 56 times.
56. And even those hypotheses you sometimes hear about cosmic rays affecting cloud formation, the scientific consensus considers them too weak to significantly impact Earth's climate. It really puts the primary drivers of recent climate change into perspective.
Okay, so it's clear that this exploration isn't just pure science or, amazing engineering. Our sources make it abundantly clear that money, politics, human resources, commitment, competition, and cooperation are all key elements. They define our push into space. What's one of the primary historical drivers that really stands out?
Well, historically, a major motivation, especially during the Cold War, was deeply rooted in geopolitical competition. It was, frankly, the desire to beat the Soviets in the battle for international status and prestige.
Right, the space race.
Exactly. The U.S. satellite program, Vanguard, for instance, it was designed not just for scientific discovery during the International Geophysical Year, but also strategically to establish satellite overflight as a benign activity. That precedent was critical for justifying later reconnaissance satellites.
Ah, interesting. Laying the groundwork.
Precisely.
And yet, despite all the ambition, we've never really launched these spacecraft to make money, have we? Our sources point out the profit motive is largely absent from solar system exploration. Even things like the Google Lunar X-ray eyes, they're kind of an implicit admission that a direct marketplace for deep space stuff doesn't exist yet. So this raises a really important question. Why does the public care? And why does the government continue to fund it, often to the tune of billions?
That's a question that's been debated for, well, decades. There's a famous story back in 1970. A nun in Zambia, Sister Mary Jukunda, wrote to NASA scientist Ernst Stuhlinger. She basically asked, how can we spend billions exploring Mars when children are starving right here on Earth?
A powerful question.
A very powerful question. Stuhlinger's detailed, really heartfelt response outlined several justifications, things like technological spin-offs, inspiring the next generation of scientists and engineers, the pure quest for knowledge. It became a kind of litany for space exploration advocates. It's a powerful and often cited defense of the work.
But public interest can be incredibly fickle, can't it? I mean, we saw media hordes for Viking and Voyager landings, massive web traffic for Pathfinder and Curiosity. Carl Sagan's Cosmos reached millions. Yet tellingly, major TV networks didn't even break into programming to show Curiosity's landing live in 2012. It really makes you wonder about the public's connection to space today. Is it waning?
Well, it highlights a core tension, perhaps, and maybe a deeper societal shift. The definitions of exploration itself have evolved. We don't really talk much about explorers on Earth anymore in the same romantic, individualistic way, do we?
No, not really.
So it raises the question, is space exploration losing some of its romantic appeal when mission names shift from the poetic, Mariner and Voyager to the more technical, almost bureaucratic Mars Climate Orbiter and Mars Science Laboratory? Does it become harder for the public to connect emotionally?
That's a really interesting point. The naming matters.
It might.
Our sources also reveal the raw financial realities. NASA's budget, while it sounds vast, is actually a tiny fraction of the overall U.S. federal budget. In 2010, for example, just the interest on the U.S. federal debt cost $414 billion. That was roughly 23 times NASA's entire budget that year.
Exactly. It puts it into perspective. And for much of its history, planetary science at NASA, even when it was dominant in the 70s, has had to constantly compete for resources internally. Compete with astrophysics, earth science, heliophysics.
Right.
This internal competition, alongside the external budget pressures, led to strategies like the faster, better, cheaper, or FBC approach, championed by Administrator Dan Golden in the 1990s.
I remember that phrase.
Yeah, the idea was low-cost missions, streamlined teams, use heritage systems, stuff off the shelf if possible. Now, FBC itself was eventually abandoned after some high-profile failures.
Like Mars Climate Orbiter, Polar Lander.
Exactly. But programs born from that era, like the Discovery program, a platform for small, focused missions, endured and proved very, very successful. Think Pathfinder, Messenger, Kepler.
So what does this all mean for the overall direction of space exploration? It really suggests that decisions are often deeply political, doesn't it?
Absolutely. NASA administrators are political executives. They are constantly balancing pure scientific goals with what the political process will actually allow, what Congress will fund. They effectively act as a bridge, translating between the scientific community and the political realities to try and maintain momentum for these incredibly long-term, big science efforts, like Mars exploration. It's a tough job.
Okay, moving on. One of the most compelling whys for solar system exploration, certainly one that captures the public imagination, is the possibility of extraterrestrial life. Our sources note evidence of liquid water on Mars, Europa, Enceladus, liquid hydrocarbons on Titan, all pointing to potentially habitable environments. What does this search bring up in terms of, practical considerations?
Well, the search for life immediately brings up really important ethical and scientific considerations around what we call planetary protection.
Planetary protection, okay.
It involves two key aspects. One, protecting other solar system bodies from contamination by Earth life carried on our spacecraft. Two, protecting Earth from potential extraterrestrial life forms if we ever bring samples back, for instance.
Oh, okay. Both ways.
Exactly. Forward contamination and back contamination. For instance, NASA deliberately deorbited the Galileo spacecraft into Jupiter's atmosphere at the end of its mission.
Why Jupiter?
To absolutely prevent it from accidentally impacting Europa, one of Jupiter's moons that has that subsurface ocean. They wanted to keep Europa pristine for future life-searching missions. Can't find alien life if you've accidentally seeded it with Earth microbes.
Makes sense. Okay, here's a truly surprising fact from our sources. One of those space legends that just refuses to die. The story of Streptococcus mitis bacteria potentially surviving on the moon. On the survey of the third camera for 31 months. Sounds like something out of sci-fi.
It's a fantastic example, actually, of how scientific understanding evolves and how persistent a really compelling narrative can be. The story dates back to the Apollo 12 mission in 1969. The astronauts recovered parts of the old Surveyor the Third lander, which had been sitting on the moon since '67.
Right.
A 1970 NASA report initially claimed that S. mitis, a common Earth bacterium, was cultured from a piece of foam insulation inside the camera.
Wow.
But later, more rigorous analysis, and frankly, most NASA officials today no longer support this claim. The overwhelming consensus now is that it was almost certainly post-flight contamination in the lab after the camera returned to Earth.
Contamination on Earth.
Correct. Yet you're right. That original, more dramatic story bacteria surviving nearly 3 years in lunar vacuum and radiation, it still pops up everywhere. A NASA.gov webpage as recently as 2012 apparently still reported the microbe survived and came back to life.
It really highlights the challenge, doesn't it? Definitive proof versus a good story versus public perception.
Absolutely. And this knowledge that microbes can survive extreme terrestrial environments, deep sea vents, Antarctic ice, high radiation, that certainly fuels concerns with all the terrestrial junk, as some call it, deposited on Mars by various space agencies over the decades. Well, it's a valid scientific question. Has the red planet already been contaminated with Earth life? Could we mistake our own microbes for Martian ones?
A sobering thought. Okay. Beyond the scientific and political realities, space exploration has always had this strong cultural dimension, hasn't it? Especially when it comes to potential threats from space.
Oh, yeah. Think killer asteroids. Our sources discuss how this narrative is just incredibly prevalent in popular culture. Blockbuster movies like Deep Impact and Armageddon, documentaries, TV series.
We all know them.
Right. It reflects these deep-rooted societal fears, maybe a fascination with existential threats, end-of-the-world scenarios.
But here's the aha moment for me, reading through this. It genuinely surprised me. Despite these sensational media portrayals, actual public opinion polls show a very different, perhaps more nuanced story. A 2018 Pew Research Center poll showed monitoring asteroids was the second highest priority for the public in the U.S. civil space program, second only to climate monitoring.
That's significant.
And a 2019 Associated Press NORC poll found 85% of respondents considered it moderately to extremely important for NASA to monitor asteroids and comets that might impact Earth.
See, this really contradicts the easy assumption that people don't care because they're unfamiliar with the threat or because it seems too sci-fi. The public is clearly aware and concerned. They see it as a core NASA job. What's also fascinating is how these fictional narratives, the movies and shows, often inflate NASA's role in defense. They often downplay the Department of Defense's actual contributions in detection and tracking. And sometimes they highlight science's limitations. Frequently, the asteroid impact is just used as this dramatic backdrop for human drama, rather than being the main scientific or technical focus. It definitely shapes public perception, but maybe not always in accurate ways.
Interesting. Okay, so it's clear that space exploration is this massive undertaking requiring incredible resources, and our sources really emphasize that international cooperation is becoming not just, an option, but an absolute necessity, especially for those high-priced, incredibly complex missions like Mars sample return.
It truly is. The path forward is collaboration. The Global Exploration Strategy, for instance, developed by 14 space agencies worldwide, provides this shared vision for robotic and human space exploration. It focuses on destinations where humanity might one day live and work. Now, it's a non-binding forum, but it's critical for coordinating efforts, sharing lessons learned, and fostering interoperability.
Interoperability, meaning?
Making sure that different systems and technologies from different countries can actually work together seamlessly. Think about global standards for mobile phones or cars, same idea, but for spacecraft and habitats. Docking ports need to match, suits need to connect to different airlocks, data needs to be exchangeable, stuff like that.
Got it. That makes sense. This marks a huge shift from the early days then. Early cooperation sometimes had its bumps, right? Like the Ulysses mission.
Oh, yeah. Ulysses, the solar polar orbiter. The U.S. probe component was canceled due to budget concerns, which caused quite a stir with the European partners. But ultimately, it became a crucial learning experience for Europe, spurring their own independent capabilities and paving the way for much stronger future partnerships. Sometimes friction leads to progress.
And we're already seeing this collaborative approach in action with current plans, aren't we?
Absolutely. Beyond the success of Cassini-Huygens, there are active plans from Europe, Russia, China, India, the UAE, all for future solar system exploration. Robotic exploration is consistently highlighted by everyone as the key first step gathering vital intelligence, testing technologies before committing to much more complex and expensive human missions. This global collaborative approach is really the only practical way forward for the truly ambitious endeavors.
This entire deep dive really makes you think about how our exploration of space just continues to evolve, constantly pushing the boundaries of what's possible, not just technologically, but also in how we work together globally. And that brings us, I think, to the end of this deep dive into our solar system. We've seen how a single mission to Venus, Mariner 2, sparked decades of incredible discovery, driven by this complex mix of scientific curiosity, geopolitical competition, and just that sheer, undeniable human urge to explore.
Yeah, from those initial flybys to sophisticated rovers drilling into Mars, from searching for life on distant icy moons to uncovering the true nature of our sun's power, and even navigating the sometimes theatrical public perception of killer asteroids. It's really a testament to the dedication of thousands and thousands of people across many nations.
So what does this all mean for you listening in? As we stand on the cusp of maybe extending human presence beyond Earth's orbit in a more permanent way, consider this. Our journey into space has always reflected not just how we do it, but crucially, who does it? With more nations, and now even commercial entities, joining the ranks of spacefarers, how might the very nature of exploration itself continue to transform in the decades to come? What does exploration mean when it's not just superpowers doing it? Something to think about.